The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, today we're going to talk about what do the spectra look like? What are the typical shapes and sizes? And what do you really need to know about the various kinds of spectra that you will encounter? This isn't going to be about the theory of the interaction of radiation with matter. This is going to be just a user's guide to what do you expect to see. And so we have three kinds . Three kinds of spectra, and they look very different. And the strategy that you use to assign them is very different. And there's a sociological aspect to that. This is why people who are microwave spectroscopists very seldom are interested in the other areas. And each of these, the spectra are so different in first appearance and the approach to them that there tends to be no crossover between these very closely related areas of small molecule spectroscopy. So I'm going to try to give a sense of these, a quick overview of these three different kinds of spectroscopy. What are the patterns that you'll find in the spectrum? And what are the typical sizes of things? And how do you make assignments? Okay. So we spent a fair amount of time talking about the central equation that governs the intensity of transitions. And the same equation applies for all three kinds of spectra, but there are different terms that are important. In the rotational spectrum, the spectral region is in the microwave and millimeter wave region. And one thing that makes this really special is that in these spectral regions, you don't use a hot wire or some kind of incoherent source. You use an electronic oscillator. And so the spectra are generally recorded in absorption, except if you're looking at the stars, then you're looking in emission. But the device you use to record the spectrum is an oscillator that is electronically controlled. And there's a very beautiful consequence of that. An oscillator is tunable over maybe 10 or 20% of its bandwidth. And so because of that, you can't see a pattern. You're generally going to be only able to observe a little tiny piece of spectrum. And normally when you assign a spectrum, you see a big pattern, there's some repetitions, there's some characteristic shape. But in a microwave or pure rotation spectrum, you just see a couple of lines. And you have to somehow figure out what to do with those lines. And that's really different from the vibration rotation and the electronic spectrum. And so I'll talk about that, and I'll talk about what appears in a microwave spectrum and how does it depend on things that you can control. In a vibration spectrum, it's really trivial, because the source you use generally to record a vibration rotation spectrum is an incoherent hot wire or some kind of a glow bar or something that emits a continuum, and you absorb the radiation. And you see, you can have as broad a bandwidth as you want, and you can see the whole characteristic pattern. And the pattern is really simple. And so here you have no pattern. For the vibration rotation spectrum, you see a pattern which practically assigns itself. because nothing is covered. That the key regions of the spectrum are in the open, and you can simply count lines. And you can say, well, this is the R branch, and this is the P branch, and it's not hard. Of course, every time, whenever something is easy, you go to a bigger molecule or you do something and you make it hard because if it's easy, well, why bother? I mean, leave that for people who are not educated at MIT. I mean, here, but it starts out being simple. The key patterns are present. In an electronic spectrum, because of something stupid, that the rotational constants for the upper state and the lower state are very different, the spectrum is really hard to assign because bands overlap each other. You can't follow branches back to the beginning. That you are stuck with having to make other kinds of, use other kinds of tricks. So these are three tactically very different sorts of problems. And that also is why people don't tend to work on all three. Okay. So let's begin with some notation. Single prime, that means upper state. Double prime, that means lower state. I don't know why, but that's what it means. And there's another thing, upper state first. Whenever you're talking about a transition, it doesn't matter whether it's done in absorption or emission, you're supposed to say the upper state first. And sometimes you can use words like from and to distinguish absorption or emission. But usually the important thing is, if you say the upper state first, then a spectroscopist will be able to load the information you're giving him. If you say it the other way around, they have to somehow stop and reload, and it's very, very annoying. So we have upper state first, we have single prime and double prime. What else do we have here? We have the alphabet for branches, rotational branches. Now, rotational branches, there's a lot of information in the way you label a rotational branch. But generally, what you do is you say, I'm going to label a line in a branch by some pattern-forming quantum number, which is usually J, but doesn't have to be. And so we have a delta, well, let's call it delta Z, because Z is never used as a pattern-forming quantum number. And so 2, that means Z for the upper state is larger than that for the lower state. That would be called an S branch. And delta Z of +1 would be called an R branch. 0 would be called a Q branch. -1 P. -2 O. It's boring, but it's beautiful because you're able to talk about the most important thing in the spectrum, and you give it a letter and everybody knows what it means. And it doesn't require that you know what the quantum number is, just that there is some pattern-forming quantum number that comes in an expression like, well, I'll do this, where you have a constant times this form. And in various Hund's cases, this is J or N or something else. But the thing that's easy to know is how does the pattern-forming quantum number change? Now, photons have an angular momentum of 1, and so you expect that J can be, J is the total angular momentum. The molecule eats a photon. It can change its angular momentum by plus or minus 1 or 0. So why am I putting 2 and minus 2, and I could go farther? Because it's not J always. And that's one of the beauties of spectroscopy. You eventually, you put labels on things, and sometimes you say, I'm done. And sometimes you say, I need to know more, but I have something that I really do know. And one of the really, the things that I consider to be beautiful about spectroscopy is how the notation is capable of describing incomplete information, or incomplete knowledge. And that as you know more, you can then go deeper into the notation. So it's a special thing. Okay. So the smallest of the things that a molecule can do that they generally do, so we're excluding hyperfine, is rotation. And the expression for rotation is generally F, and you put a V on there to say it's a particular vibrational level. You might put another index to say what electronic state it is. So the rotational energy levels generally go like that. And so if we're going to be observing a rotational transition, we're going to be looking at FV of J minus FV of J minus 1. And you can do the algebra, and you get 2BJ minus 4J cubed D. Now, so the transitions that you expect in a rotational spectrum are going to follow this nice rule where the difference, the transition frequencies are given by a constant times the higher J. Now, what about this? Can we ignore it? Well, D, we derived from perturbation theory for B cubed over omega squared, the Kratzer relationship. So B is 1 and omega is 1,000, so this is on the order of 10 to the minus 6. So this is always ignorable if you're looking for patterns. It's not ignorable if you're looking to be correct, but it's ignorable if you're starting to put labels on things. So you're looking for a pattern of lines in the spectrum. So that's 2B, that's 2B, that's 2B. And so there'll be a pattern of lines, and let's say here's 0. And so the microwave spectrum would be, if you could look at all of it, would be a series of equally spaced lines separated by 2B. And if that were true, then there would be no challenge whatsoever, because this spectrum would assign itself. Because not only is there a unique thing at 0, like nothing, but the spectrum starts at 2B, and so what you want to know is B, and there's no ambiguity. But because of the limitations of electronic oscillators, you can only scan over a small piece of the spectrum. And usually, the oscillator, the region that you're able to access with the oscillator is sufficiently wide that you'll catch one rotational line. And it's very hard to see a pattern with one thing. So what do? How do you know what it is? Well, this is you're operating in a world where people do know stuff. And you know a typical value for bond lengths, and you know what the masses are. You may not know which molecule you're looking at, because sometimes when you generate molecules, you do it in a discharge or in some sort of a violent way, and so you don't really know what you made. And so you don't really know what molecule this line that you observed in your spectrum is. But what you generally do, especially for microwave spectroscopy, is that you say, well, what is it likely to be? And what is the rotational constant that this molecule is likely to have? And if that's true, what J does that line belong to? Or what J did J minus 1 to J does it belong to? And so really you want to know what 2B is. And so you make a hypothesis, and then it tells you, okay, let's look at the next line up or the next line down by buying another oscillator or borrowing one. And so you make a prediction. This line is at 6B, and so the next line up will be at 8B, so at 4/3 the frequency of this one. And so, but if you're wrong, then you won't see anything here. Okay, so there is, because the pattern, you see only a little bit, but the pattern is so simple, you generally make some sort of a prediction, and then you have to verify the prediction. And one of the things about spectroscopy that's really special, and I think unique in physical chemistry, is that when you have the correct assignment, you are 100% certain that it's correct. Because if you can observe these two, the second line or a confirming transition, whether it's the next one up or an earlier, just any other oscillator that produces another line in the same spectrum, then you know for sure what B is, what J is, and knowing B, you have a pretty damn good idea of what the molecule was if you didn't know. I mean, if it's just a permanent gas, well, it's easy. But people did all the permanent gases in the early days of microwave spectroscopy, and so there wasn't really much to do to earn a living if you don't do something violent where you don't know what the molecule is. Okay, but there's more details. And these are something that's really beautiful about microwave spectroscopy. Okay, here's the V equals 0 level. And here is a V equals 1 level. And this has a rotational spectrum. And this has a rotational spectrum. And the rotational constant for V equals 1 is just a little bit smaller than for V equals 0. So V is BE minus alpha E V plus a half. And alpha is usually about 1% of B. So D is usually, a part in a million of B, but alpha is 1%, roughly. And now, this is going to be a big energy difference compared to KT. And so if you're working in an equilibrium system, then you're going to, you may not see any hot bands, that's what they're called, but you may see hot bands. They'll be very weak. And so what you'll see is your normal rotational transition, and then next to it you'll see a really weak line which say is 1% the population, because e to the minus h omega over kt on the order of 0.01 or something like that. And so you could figure out what sort of temperature, what sort of omega. But I mean, you're going to see these weak lines. They're going to be really weak. But one of the beautiful things about microwave spectroscopy is it's very sensitive. And so if you have really good signal to noise, you're going to see a hot band.
Can you use anything about the observed intensity? That is to say, we were talking before how often intensities are really hard.
Yes.
But is that different in microwave spectroscopy where you can...
Well, if you have equilibrium, well, yeah, I mean, that's one of the things about having different spectroscopies that don't cross-link. So a microwave spectroscopist might say, I'm going to, since I know the temperature, I'm going to use this relative intensity to determine omega, the vibrational frequency. Well, you know, that's got to be crazy. Or, and this is not crazy, they use this. You measure the centrifugal distortion. Remember, you can measure microwave transitions to easily a part in 10 to the 6. And so if you measure 2 rotational transitions, you've got a pretty good purchase on D. And if this equation, which comes from perturbation theory, is valid, then you have a pretty good measure of omega. And so microwave spectroscopists often claim to measure vibrational frequencies. I think that's ridiculous, but it's much less ridiculous than getting it from the intensity. Okay, so there are these hot bands. We also have other isotopomers. I mean, the rotational constant is proportional to mu over r squared. And so that's the internuclear distance. This is the reduced mass. And so if you have a heavy isotope, that means mu will be bigger than for the normal isotope, and that will make B smaller. And so there are also going to be some things over here that are isotopic. They're not temperature dependent. So if you could change the temperature by a factor of 2, or whatever factor, you're going to change the hot band intensities relative to the cold bands, but you're not going to change the isotopic bands.
Of course, you might introduce new hot bands.
You will introduce new hot bands, but since the rotational constant depends on V linearly, the next hot band is going to be down here and here. So so you will see more than one hot band. Okay. One more thing. I mean, yeah. So, two more things about pure rotation spectra. Suppose we're observing a J minus 1 to J transition. What will be the temperature dependence? So the transition, the absorption, depends on the difference in population. It depends on the difference in population between J and M levels, because you have a particular JM, you're going to a different J, same M. And so you want to know what is the difference in population between J levels for a given M. So that tells you what you do with the Boltzmann degeneracy, the 2J plus 1 degeneracy. You forget about it. Okay, so what is so what does temperature do? Well, one thing it does is it says the fraction of the molecules in the sample that are in J equals J or J minus 1 decreases as the temperature goes up because the rotational partition function increases. And so there's going to be fewer molecules in the two J levels you care about as you go up in J. And so you're going to get a 1 over T dependence for that. And then there's a difference in Boltzmann population between these two levels, and she'll get another 1 over T dependence. So you ought to be able to derive that. So the sensitivity of microwave spectroscopy is very much compromised by going to higher temperature. Now, we do experiments in our lab at a temperature of 5 Kelvin or something like that. And that's because we use a supersonic jet. But it's awfully tempting to say, well, suppose we photolyze a molecule. Instead of using an equilibrium system, we're making molecules in rotation and vibrationally hot levels because of some photolysis event. Well, first of all, they're not going to be Boltzmann, but they're going to be hot. There's going to be most of the population in relatively high J. And so microwave spectroscopy is a fantastic tool, but you have to keep in mind this 1 over T squared. And if you sort of approximate the rotational population of a fragment as 1,000,000 degrees, you know you're really in trouble. Okay, but another thing that's wonderful about microwave spectroscopy is that suppose you have a nice equilibrium, a non-equilibrium source, a discharge or photolysis, and you make molecules in many vibrational levels. Well, Mr. Microwave says, okay, I like that. I'm going to have now a real spectrum. Because there'll be a whole bunch of lines. All of the J to J plus 1 transitions, regardless of V, will be roughly in the same oscillator. And so you'll be able to see a whole bunch of transitions, and they'll more or less assign themselves. And the intensities will tell you what the population was in the initial vibrational level, and that's telling you something about the dynamics. And so this is a fantastic tool for looking at dynamics that has not really been exploited.
How do they assign themselves? Their absolute positions?
Well, if it's a diatomic molecule, it's really trivial because the rotational constant depends linearly on V. It decreases linearly in V.
So whatever the first one is, assume is V equals 0?
Generally, you can do that, yes. It's very rare that that you don't have V equals 0, but I mean, it's possible. But you see a sequence of transitions of that are more or less equally spaced, and you pretty much know those are different vibrational levels. Now, in polyatomic molecules, you will have each of the vibrational modes changing the rotational constants in different ways, but each linearly. So it'll be a little bit more complicated. There'll be families of related transitions, but it's a wonderful thing, and this is something that we're going to be exploiting. And but it doesn't push the technology of microwave spectroscopy because all of these transitions are pretty close. But if you have really accurate measures of the relative intensities of lines, then you really have accurate measures of the populations, because the only difference, what you need to know is what is the dipole moment, permanent dipole moment, and what is the population. And that's what you want to measure. You measure the intensity, and so you get that. Now, the dipole moment might change with vibrational excitation, but you can also measure that by doing the Stark effect, or you can ask a quantum chemist to calculate. Got to keep them employed. Okay, so let's stop talking about microwave spectroscopy. I love microwave spectroscopy, and I don't really like vibration rotation spectroscopy, which is what we're going to talk about next. So that depends on the dipole moment function being different from 0. And so if you have a polyatomic molecule, some vibrations might have a non-zero dipole derivative. But for a diatomic molecule, if it's a heteronuclear molecule, this will be non-zero. And if it's homonuclear, it'll be 0. So if we want to look at a rotation vibration spectrum, we need to know an expression for the vibrational energy levels. And we already know the expression for the rotational energy level, so I won't write it down. And we know that BV is BE minus alpha E, V plus a half. Now, one little note of this is a single symbol. It's not a product of two symbols. In polyatomic molecules, although we use models, diatomic-like models for them, we call this first anharmonicity constant x, and it doesn't have a minus sign. So it would just be plus x times this. But for a diatomic molecule, I don't know why, it's called omega exe. Why? 4 things. But you know, you get to say it really fast, and you know, it's it.
Does the E stand for something?
Equilibrium. But you know, the real thing you're supposed to, you call these things omega E and omega exe. And so that's what you're supposed to say. I don't know why. Maybe it's part of the rhythm of the language that gives you a chance to resolve the various elements. Okay, so we have these things. The typical rotational constant, I said before, was about 1 reciprocal centimeter. The typical vibrational constant is around 1,000. Okay, and you know, you can have a big range, and I gave examples in the notes of things that are really small and really large. For example, a vibrational frequency for a molecule with heavy atoms and a very large bond length will be really low. And cesium has a 42 wave number vibrational frequency, and iodine has a 215 wave number, and hydrogen has a 4400. What?
I think it's 4155.
Well, it depends. It may be, but I don't know where I got 4400, but I'm sure that I had a reason for it. Okay, so we have a simple expression for the energy levels. And let me draw the standard diagram for a vibrational spectrum. Oops. So let me leave some room. We have the rotational manifold and a big step in a vibrational. So here's one vibrational level, here's the next, almost identical. And so what we would like to know is, what is the lowest J, well, what kind of branches do you have? You have R branches and we have P branches. For a diatomic molecule, the transition moment is in the Z direction, and so delta omega has to be equal to 0. And so when delta omega is 0, there's no Q branches. Well, what would it mean to have a Q branch anyway? Well, actually, we could have Q branches, but so weak Q branches. I meant to say that about rotational spectra. You shouldn't have Q branches in rotational spectra, but how could you have a Q branch here? But if you had a omega not equal to 0 state, then you could have a Q branch. It would be, but it would be at very low frequency. Okay, so we have weak or absent Q branches, and so the first, we have another convention. So here's it's going to become a spectrum, and we have Hertzberg's rule: red on right.
I mean,
You're supposed to.
I do.
Do you?
You're supposed to. I do when I think of it. I mean, I have spoken in front of Hertzberg, and I have worried about certain things that I don't take as do as carefully as most. But you know, so red on the right. So let's put.
But if you're going to talk to physicists, right? Do you bother with it?
Well, you see, if I'm going to be truculent when I write a review, I often, will say, well, they're violating these Hertzbergian rules, and so anyway, so we're going to do red on the right, but it actually helps. But okay, so we have red over here, and we have the possibility of a P branch or an R branch. So a P branch, this is j equals 0, 1, 2. A P branch, the first P branch, well, we can't have a P branch from j equals 0. So the first P branch will be this one. So let's just erase that. And that would be called P1 because we label the branches by the lower state j, or the lower state pattern forming quantum number. And so here's a line. And the next P branch will be P2, and there's a line here. And so there'll be a series of lines. The first R branch will be from j equals 0 to 1. And I should have drawn it a little farther over. So I should have drawn it there. The next R branch will be from 1 to 2, and it will be a line here. So what you see, there's a gap, and there's a place where a line should have been if the pattern were regular, and these lines are separated by approximately 2b. And so this is why a vibration rotation spectrum assigns itself. If you have reasonable resolution, there will be a gap in the middle, or gap somewhere, and that will be where the Q0 line would have been. Except Q0 is illegal. And so you can see that to the red will be the P branch, and to the blue will be the R branch. And they are relatively evenly spaced lines.
You drew them with equal intensity.
I drew them on a strip. I wasn't saying anything about intensity.
Okay.
The intensity for these transitions, since the upper state is usually empty, the intensity is going to be given by the rotational line strength factor and by the rotational populations. So if I were drawing
the rotational population of the lower state.
Of the lower state. And so, and regardless of what the rotational population is, the most important thing is the degeneracy here. And so you have branches that sort of open up like that. And you get this double hump aspect. So the most important thing is that there's a gap here, and you know how to start numbering things. And the gap is also the energy of the vibrational, the j equals 0 to j equals 0 vibrational transition. And so you get a pure vibrational bit of information from this pattern. And that's really nice, especially when you are going to see what happens in an electronic spectrum. So these really do assign themselves, because you see the enough of the pattern to know what it is. And now you don't necessarily know that this is v equals 0 to v equals 1, but what else could it be? I mean, the vibrational energies are really big compared to kT generally. And so, and the different vibrational bands are near each other. And so you're going to have another vibrational band much like this, but with maybe 1% the intensity. And it's going to be shifted Where? Well, what usually happens is as you go up in vibrational energy, the levels start to get closer and closer together because of this guy. And so the next vibrational band is going to look just like this one, but it's going to be shifted a little bit to the red by 2 omega exe. And almost everything in it is going to be pretty much the same, but it'll be shifted and it'll be weaker. So it's really hard to imagine getting a vibrational assignment wrong. But people can be quite resourceful. Okay, what else do I want to say? So in the infrared or vibration rotation spectrum, there are going to be hot bands and there are going to be isotope bands. And the isotope bands, there's 2 different scalings. One is, again, B goes as 1 over the reduced mass, and omega goes as 1 over square root of the reduced mass. And so there's going to be isotope information, and you can make use of them. Okay. So, goodness gracious. I thought I wouldn't have anything to say, and I'm just so loquacious. All right, I'm an electronic spectroscopist. I don't know why, but that's what I started out doing. And I think electronic spectroscopy is really a wonderful way to look at molecules. And so let's simplify as much as we can to the simplest possible transition. Now, for electronic transitions, the states that you can see are limited by the symmetry of the electronic state. So in vibrational spectra, you have a propensity rule for vibrational transitions, delta V of 1, that comes from the first derivative of the dipole moment function. And delta V of 2 is really weak. That comes from the second derivative of the dipole moment function or some mechanical anharmonicity or both. And, but you don't normally see a long progression of vibrational bands. Here we have a selection rule on electronic states that you can see. But depending on the shapes of the potential curves, there's no propensity rule or selection rule for vibration. There are just Frank-Condon factors, which you can calculate if you know what the shapes of the potential are. Or you can model the Frank-Condon factors by having some sort of crude model that you fit to the spectrum. I mean, if you can determine B, omega, and omega x, then you have a Morse potential. You could say, I'm going to determine the constants of a Morse potential from this. And so you can then derive Morse potentials for the upper state and the lower state, and you can calculate Frank-Condon factors analytically if you want to. We have other techniques, other things, and I am going to give a lecture on the Rydberg-Klein-Rees method for deriving potential curves analytically from spectra using semi-classical approximation, but that's not for today. So we have vibrational complexity, but the worst thing is we have rotational complexity because let me just write out the equations for the R and P branches. And so in R branch, we have the band origin, and then we have a J squared term, delta B J squared. And then we have a term that's linear in J, and that's going to be 2B prime plus delta B J, and then 2B prime. And for the P branch, these, you could derive these equations very easily. Nu 0 plus delta B J squared minus 2b prime minus delta b j. So these are the formulas for the R and the P branches. And so the quadratic term, the difference in B, is smaller than, say, 2b. Now, in vibration-rotation transitions, delta B is so small that you ignore it, or you almost ignore it. And so you would never write the expression for the R and the P branch in this way. But because delta B for an electronic transition can be quite large, and it's multiplied by j squared rather than j, it can be the dominant expression in this branch formula at thermally accessible j's. And so what ends up happening is that both of these branches, well, this branch starts going to the blue because it's got a positive term here. This branch starts going to the red because it's got a negative term. But then this term gets big, and depending on the sign of delta B, depending on the sign of delta B here, this can make it turn around and go the other direction. And similarly here. So what these equations tell you, the sign of delta B determines whether the R branch will just continue on going like this, or come around and go that way and walk over the P branch. And so when you have these band heads that occur, the lines get closer and closer and closer together. You can't resolve them. And then they turn around and you've lost track. And then they walk over the zero gap, which is the thing that you wanted to see. And then they walk over the other branch. And so it makes assigning the transitions hard, but not impossible. In fact, pretty trivial. I'll talk about that next time. But it's a kind of a tedious thing. You sort of think, well, why should I be bothering with something like that? Because we just looked at two different kinds of spectra, and it's trivial. But now these simple formulas, but it says big trouble. So anyway, electronic transitions will have.
Can I ask a question about that?
What?
So so if you expand the 2b plus delta bj terms down for both R and P branch,
Yes?
both of them have a delta bj term that goes the same way, right? That doesn't matter, right? I mean, the difference between the R and the P branches is one has a 2b prime j and the other has a minus 2b prime j, but both have the delta b terms going in the same direction.
Yeah, I may have made an algebraic mistake. I don't think so. The delta b can have either sign. And the important thing, it doesn't really matter what this is. The important thing is that this delta b, j squared, is going to get big compared to 2b before this does.
Oh, because there's a j squared.
Right. Right, and as a result, the sign of delta B determines what the band will look like, and because delta B is larger than 1% of the value of B, which it would be for a vibrational transition, because alpha is 1%, this could be half of B. And so you get branches, you get bands that basically look like this or like that. This is red on the right. And so this is called blue degraded. And this is called red degraded. This is the more usual situation. This means B prime is less than B double prime. And this means B prime is greater than B double prime. Why is it? usually when you excite from the ground state to a higher excited state, you've reduced the bonding. It's usually a bonding to non-bonding or a bonding to anti-bonding. So it's very common that the upper state B value is like this. So one of the things that you get for free when you look at a band in the electronic spectrum is B prime larger or smaller than B double prime? But that's all. Everything beyond that you have to really work for. Because somewhere lurking in here is the band origin, covered up by the most dense forest of lines. And because the a branch turned around and came back on itself, you lost count. So you can't, and you don't know where this is relative to the origin, although it's a common approximation to say, well, since this is something I can measure really well because it's a sharp structure, I'm going to measure the band heads rather than the band origins. But that just folds some unknown rotational information into the expressions for the vibrational levels. So the way you assign these things is that you resolve the individual lines and you look for rotational combination differences. And there are two kinds of there are upper state rotational combination differences and lower state rotational combination differences. And they basically say, so I mean, you have this sort of situation, that's a combination difference. Or you have this kind of a situation, and that's a combination difference. Okay, but now, if you think about this for a second, you say, what good does that do me? I mean, I look at a bunch of lines in the spectrum, and certainly a combination difference is a difference in frequency of two lines. Which two? Well, it's cheating because there's no repetition here. Now, if you know the rotational constant of the lower state, well, then it's child's play, because then you do know what combination differences you could have, and then you go looking for them. And if your resolution and precision is sufficient, then you can make assignments. But usually, you don't know, and you have to build up an assignment by saying, okay, we have two different vibrational bands with a vibrational level in common, and then there will be one combination difference, a duplication of combination differences between these two bands. But you don't know when you record a spectrum whether they're linked. So it says, well, I'm really in trouble here. I can't make any sense of this until something lucky happens, or until I go through the most incredible donkey work to find these repeated intervals. And it's really, really hard and boring. And so next time I will take you into the heart of darkness. I couldn't come up with it. And I will show you the method called the Lagerquist strip. And this is not a burlesque show. This is a magical method that Anthony Mayer also uses. You've probably some of you saw Anthony sitting in the lab and assigning spectra using a piece of paper and a ruler. That's called the Lagerquist strip. And I will tell you about that and other methods. And then the next lecture I will show you how you get the same information much more easily using laser tricks.